Okay, I think they started. I see people are still streaming in. Let's wait for a few more minutes. Okay, since it looks like we have hit a plateau in the number of attendees, probably a good time to start. Today, we're very happy to have Jianhua Gong, our new, well, relatively new postdoc fellow at IGPP as our seminar speaker. And I will let her advisor, Wenyuan Fan, to introduce her.
Hey, wow, I actually wrote something. It is a pleasure to introduce Jianhua today. Jianhua is interested in seismic and tectonic processes at active plate boundaries, including subduction zones and mid-ocean ridge transform fault systems. Jianhua obtained her BS and MS degrees from Peking University. Before joining my group, Jianhua obtained her PhD from Hui, primarily working with Jack McGuire, who happened to be my postdoc advisor at the time. Jianhua and I sailed together on a research cruise for about a month, and we are still friends after the cruise. It seems that we can work together. During the cruise, we deployed about 50 OBS instruments to study mid-ocean ridge transform fault systems. Jianhua joined IGPP earlier this year in February, quite recently, but she has been very productive and has submitted a paper to GRL. I think that's her focus today. So Jianhua takes the stage.
Yeah, thank you, William, for the very nice introduction. Hello, everyone. So today I'm very happy to present the study that I have been working on since I came here in February. So in this work, we use microseismicity to study the atypical plate spreading behavior along the Quebrada transform fault on East Pacific rise. This work is in collaboration with Wenyuan and Ross, and I would also like to thank Professor Peter Scherer for teaching me doing earthquake locations, and Jack McGuire, John Collins, and the QDG cruise team for collecting the data that is used in this study. So oceanic transform faults plays a key role in plate tectonics. They offset the spreading segments and also accommodate the relative motion among adjacent oceanic plates. Oceanic transform faults also generate fracture zones. Also generate fracture zones, which are fossil fault traces outside the major spreading region. People used to think oceanic transform faults are simple plate boundaries, just two plates sliding against each other. However, with higher resolution C4 bathymetry and more other geophysical measurements, we started to see more features of the C4, like what is shown here in this map. And also in this way, we started to gain more and more insight into how plate spreading is actually occurring along the mid-ocean ridges and transform faults. So our study area, East Pacific rise, is the ultra-fast spreading center. It has a full spreading rate of 120 to 150 millimeter per year. The map on the left showing you the major plate boundaries, oceanic ridge near the north and south American plate. East Pacific rise is the plate boundary between the Pacific plate and the Cocos and Nazca plate. So there's a distinct difference in the geomorphology between slow and fast spreading ridges. Slow spreading ridges is characterized as by a deep valley, but fast spreading ridges are characterized by high elevation ridges. And the area that we are looking today, the Quebrada transform fault, is located in this rectangular shape, which is the first major kink along the East Pacific rise south of the coastal ridge. Here is the bathymetry map of the Quebrada transform fault. The Quebrada transform fault is usually considered together with the Discovery and Gophar transform fault because of their close in space. As you could see from this bathymetry map, none of these three transform faults are a single fault trace. All of them consist of two or more small segments. For example, the Quebrada transform fault has 4 segments connected by 3 short distance spreading centers, which are S7, S8, and S9. So the first part of this talk, I will focus on the Quebrada transform fault, and later I will spend a little bit of time compare Quebrada and Gophar and discuss the special characters of the Gophar transform system as well. Also from this bathymetry map, you can see that the Quebrada fracture zone is characterized by deep basins, which are shown by the blue color here, which is in contrast to the topography we just discussed in the previous slides, that fast spreading ridges should be characterized by high elevation ridges. And okay. So besides the topography anomaly, Quebrada transform fault has other atypical features as well. So this map shows you the depth to the 1,000-degree isotherms along the 3 transform systems, and compared to the other ridges under Quebrada, the isotherm to the 1,000-degree isotherm is fairly deep, indicating the cold temperature beneath Quebrada. Moreover, Quebrada is characterized by thin crust with only about 4 kilometer thickness, compared to other ridges, which are usually about 6 kilometers or higher. This is a very thin crustal thickness. And another reason that we care about alternate transform faults is related to earthquake hazards. So everyone living in Southern California understand why we need to care about San Andreas fault. And you perhaps know about this park field experiment, where people in Southern California know that the park field segment of the San Andreas fault failed repeatedly in the similar area. And in the early 1980s and 1990s, people know that in 1966, there is an earthquake, magnitude 6 earthquake occurred. And the next magnitude 6 was expected to build around 1994. So a lot of instruments were accumulated around the park field area to wait for the next big event. However, the fault failed in 3 successive smaller events without filling in a big one. And the big one didn't occur until 2004. So on continental transformed settings, is very, although we know that earthquake is due to the energy accumulate and release. However, you hardly get a periodic behavior of earthquake cycles. But this is not the case for Gophar. And for the QEG system. So in this map, I'm showing you the location of magnitude 5 and above earthquakes along the fluid transform fault system. So each circle represents an earthquake. And if we plot those earthquakes with over time, and you can see that this earthquake happens quite periodically. So magnitude 6 events occurred every 5 to 6 years along the Gopher and the Discovery transform fault. So this provides a great opportunity for us to capture the earthquake rupture process of a moderate size earthquake. However, for Quebrada, we don't see a lot of magnitude larger than 5 events. So given they are close in space, what happened to Quebrada that causes a lack of large magnitude events? So with those anomalous behavior along the Quebrada transform fault, we will use OBS data to investigate the plate spreading behavior along Quebrada. So the data that we will use in this study come from a 2008 OBS experiment. There were seismometers deployed along the three fault traces. However, the data along the Quebrada transform fault were not analysis yet, and we took these advantages to test the data and try to answer the question: how is plate spreading accommodated along the multi-strand quiet Quebrada transform fault? So here is a zoom-in view of the topography of Quebrada. Quebrada, as we just talked about, it can be divided into 4 transform segments, which are labeled Q1 to Q4 from north to south, and they are connected by 3 intra-transform spreading centers S7 to S9. And the whole area is characterized by a deeper basin, especially to the north and south of Q2. And the transform fault is bounded by high elevation flanks to the north and south. I also highlight the location of the Q3 fracture zone, which we will discuss later. And for doing earthquake detection, location and relocation, we adopt a procedure as follows. So the data, so these triangles indicate the location of the stations. One of the station didn't function very well. It's the Q08. These stations started to run out of power since August in 2008. So we'll only use we'll discuss the time period between January to August. And during this time, only 2 large magnitude events were reported by the ISC catalog, which all occurred on January 6th in that year. And processing OBS data are used to be thought very difficult because it's hard to pick the PNS phase arrivals on OBS data. And in our study, we use a machine learning phase picker developed by Masawi et al. And this method actually works very well on our data set. And now I can pick the PNS phase arrivals on my own laptop with this data set in about a week's time, which greatly reduced the work we need to picking seismic arrivals. And later, we used the method developed in Professor Peter Shearer's group to conduct the location and the relocation. So in total, we have detected and located 24,000 earthquakes during the 8 months, and the location of the seismicity is plotted on this map. As you could observe, the earthquakes are unevenly distributed among the 4 segments. So on Q1 and Q4, we have relatively dense earthquakes. And on Q3, we have moderate amount of earthquakes, but on Q2, we are short of oh, sorry. We are short of seismicities, and why is that? So the short of seismicity indicates that the Q2 segment is probably sliding aseismically, and this aseismic sloping behavior on oceanic transform fault has been studied extensively, and and it has been reported that about 60 to 70% of the slip on global oceanic transform faults are slipping aseismically. And for our study reason, we infer that the Q2 segment slides aseismically can be due to either the thin crust thickness to the north and south of it, which doesn't have because of the crust thickness is so thin, it doesn't have a big area to generate enough earthquakes, and also because of the basin structure, it can be less normal stress attached along this fault, which also favor aseismic slip. And so here I just plot the seismicities over an intensity map to highlight the location of the earthquakes and separate the seismicity that are associated with different fault traces. And I will discuss each of them one by one. So after Q2, the next, okay. So here's a summary of what we are thinking around Q2. So around Q2, we think that the fault is surrounded by deep basins, and the fault is slipping aseismically. Then let's move on to transform fault Q3. An interesting thing that we discovered on Q3 is that there are abundant of seismicities along the fracture segment of Q3. This is very contradictory to our traditional view that fracture zone doesn't have slip on it. And here, the top map is a map view of the distribution of the seismicity, and the bottom is a depth view. And there are about 1,000 events located on this fracture zone. So, what is the cause of this fracture zone seismicity? So I later plot the seismicities in XY coordinates and rotate it so that the trace of Q1 and Q4 are relatively parallel. And in this map view, you can see that the trace of transform fault Q3 actually has a slightly angle compared to Q1 and Q4, indicating that it is not parallel to the spreading. It is not normal to the not parallel to the spreading direction. And this made me think that maybe some small scale plate rotation is within this Quebrada transform system that cause relatively slip around the Q3 that generating these seismicities along the fracture zone. So plate rotation is not a new idea. It has many features of the seafloor has indicating where plate motion changes or plate rotations has occurred. This is one of a pioneer work by people from Swiss, where they studied the fracture zones of in the Northeast Pacific Ocean, and the fracture zones. For example, the Mendocino and the Murray fracture zone, they are not smooth traces. However, it can be separated into a few segments, and these segments indicating that the plate spreading direction has changed in about 5 episodes with the generation of these fracture zones. And plate motion can, plate rotation can also occur in shorter time ranges. Here is an example showing you two other transform faults, the Clifton and the Sequorial, along the northern part of the East Pacific rise. And these two nearby transform systems are characterized by different geomorphology features. Clifton is characterized by a high radius along the transform fault. However, Sequorial was split into 5 segments. And what causes this? People have inferred that recent plate rotation between the Pacific plate and the coastal plate has caused these changes in the geomorphology. And for example, so the counterclock plate rotation along the East Pacific rise will cause transpression along the Clifton transform fault, but trans-extension along the Sequorial. And these transpression faults will generate a median ridge along the fault traces, and the transtension will create spaces along the Sequorial and generate forces to split into multiple segments. And this theory has been used to explain the generation of those multi-strand transform systems. And so, and because the Quebrada transform fault is also a multiple segment transform fault system, which makes me think that it also indicates that there are relatively plate rotations between the Pacific and the Nazca plate in recent geological time period. And to look at for evidence of plate rotation, let's look at the Google map. Here I show you the rough location of this QVG system. Maybe this map is not very clear, and now we will switch to the vertical gravity gradient map, and you can, which is more sensitive to some of the topography features. And I label the Quebrada fracture zone and the Gopher fracture zone, also the major plate boundaries and the 3 large tectonic plates. So when you look at the Quebrada and Gopher fracture zone, they're relatively short. It doesn't like the fracture zones to the north of the Pacific that extend halfway into the Pacific Ocean. So what is that? Why is that? And also, south of these fracture zones, we see other features on the seafloor. So the thing is, they actually have names. So this, by looking at this Google map, it motivates me to understand the tectonic history of the Quebrada Gopher transform system. And I was lucky to find a PhD thesis by a student from Texas A&M, where she did a plate reconstruction between the Pacific plate and the Nazca plate. So we have to go back to 23 million years ago, and at that time, we don't have the Cocos and Nazca plate yet. The plate bound, the major plate is the Pacific plate and the Farallon plate. And at about 19.5 years ago, the Farallon plate split into Cocos and Nazca, and this plate breakup also is accompanied by a spreading direction change with a clockwise rotation in plate spreading change. And with that, we started to see the propagation of the East Pacific rise and also the generation of newer spreading ridges. Especially, I want to highlight this Galapagos rise north of this Mandana fracture zone. So as time goes, the East Pacific rise continue to propagate to the north. And at this time, the major plate spreading between Pacific and Nazca is accommodated by this Galapagos rise. And there's also a small plate called Bauer microplate forming between the Galapagos rise and the north propagating East Pacific rise. And at around 9.5 million years ago, the East Pacific rise propagates to meet the coastal ridges, and gradually the spreading changes shift from the Galapagos rise to the East Pacific rise. And by about 6 million years, the Galapagos rise was gradually abandoned, and the East Pacific rise become the new plate boundary between the Pacific and the Nazca Plate. So, and also at this time, we started to see the formation of the Quebrada discovery and the Gulf-transform fault in this sense. And also, as you could see, the curvature of this Gallego fracture zone indicating that the Bauer basin likely undergoes some plate rotation at this period. So nowadays, the Galapagos rise is more or less abundant, and the East Pacific rise is the real plate boundary between the Pacific and Nazca Plate. So right now we understand how these different tectonic features are generated through the tectonic processes. So the QDG system is generated by the north propagation of the East Pacific rise, and its geomorphology is related to the adjusting of the East Pacific rise. And maybe it's more clear to view the QDG system on the gravity anomaly map, which clearly the QDG system marks a difference in gravity anomaly in the major East Pacific rise and to the north of it. So perhaps we're looking at the Quebrada transform fault is actually we're seeing a small transform fault under a big tectonic history, and through the generation of this QDG transform fault, we suspect that through the generation of this QDG system, it has been undergone some plate rotations to adjust the propagation of the East Pacific rise, and this tilt feature of the Q3 transform fault can be because the current undergoing plate rotation, or maybe that the Q1 and Q4 has been adjusted to the previous plate rotation, and the Q3 is still trying to catch up. So in general, we infer that the active seismicity along the Q3 fracture zone is related to some plate rotation events within the Quebrada transform system. Next, another striking feature of the seismicity location is the very diffuse seismicity along the end of this Q1 and Q4 transform fault. And so in the following time, I will study the seismic behavior of these clouds, diffuse seismicities, and what they might indicate for the tectonic behavior of the Quebrada transform fault. And so the bottom two rows showing the distribution of the seismicity along Q4 and Q1 in map view and depth view. And I highlight the locations of these two diffuse seismicity cloud. And some general features of this diffuse seismicity cloud is that it in general go dips towards the mid-ocean, towards the intra-transform spreadin center. And they are very diffusive. It's unlikely that these earthquakes are generated on some major fault surface. So later, I started to study the temporal evolution of the seismicity in each of the diffuse seismicity cloud. So the figure on the right, the first column is the seismicity plotted in its horizontal distance versus time. And in this map, you can identify that the seismicity is not evenly distributed over space and time. There are periods of burst seismicity. And the second column is the daily seismicity rate in this diffuse seismicity, in this diffuse cloud. And you can also identify a few days with much higher seismicity rate. So I select two seismicity burst events. The first one is around day 13, and these are the seismicities we identified within this temporal cluster. The two white dots indicating the two major big events reported by the international by the IAC catalog. They are because of we have the nearby stations, we can more accurately locate these events. So these events are these two events are located within this seismicity cloud, with the northern one occurred first and the southern one occurred about 2 hours later. And this event triggers the whole seismicity cluster in this area. Also, for example, for the seismicity cluster along day 69, it's burst of seismicity indicating by the daily seismicity rate, and most of the events occurred near the interaction between this diffuse cloud to the transform system. We can do similar things for the diffuse cloud in the Q1 transform fault. Again, the two columns showing you the distribution of the seismicity and its daily rate, and we identified about 17 dense earthquake clusters along this inside this cloud. And I would like to highlight 3 clouds around the days 200. These 3 clusters likely represents a migration process from seismicities in the deeper part of this cloud gradually to the intersection with the transform fault. So so these cloud, so the earthquakes inside these 2 clouds clearly show some periodic episodic behaviors, and we would like to understand what causes such seismicity behavior. And to investigate what causes the dipping structure of this seismicity cloud and its overall spatial temporal evolution, this is a study from Wright et al., which they studied the geodynamics of the multi-strand transform fault. I'm sorry this is a busy figure, but I want you to focus on the color background, which indicates the depth of the to the top of the mouth along this multi-segment transform fault, and they are targeting this securial transform fault that we talked about before. And as you could see, around the corner of the transform fault and spreading radius, we see this migration of the melt from the intra-transform fault to the nearby major spreading centers, which might indicate that the three-dimensional structure of the multi-strand transform fault can cause pretty complicated migration patterns. And this migration pattern is similar to what we have observed of the depth distribution of the microseismicity, where those seismicities are deeper near the intra-transform fault and goes shallower to the transform fault, indicating that it might be related to the melt extraction from the short intra-transform fault spreading radius to nearby large mid-ocean radius. However, if we plot the isothermal structure on top of this seismicity distribution, we see that the abundant degree isotherm is located within these seismicity distributions. This is unlikely because the 1,000 degree Celsius is too hot for brittle deformation. There should be other mechanisms that cause the diffuse seismicity in this inter-spreading center. And so here is what we infer from our system. We think that the small plate location, melt migration, and the fast spreading radius can cause a strong damage of the fault materials along the spreading center, small spreading center. And these strong damages could facilitate root circulation into the deeper part of the mantle to generate those deep seismicities. And because of the long duration of the seismicity, and this seismicity should be continuous. So only, which means that such damage should be a continual process. And we think that the small plate rotation and some ongoing small plate rotation and fast spreading is necessary to sustain the damaging of the fault material and keep the fluid circulation going on into the deep mantle. So conclusions for our part one. So we observed that Q1, Q3, and Q4 are seismically active, while Q2 likely slips aseismically. And there are abundant of seismicities found along the Q3 fracture zone. And we also observe a pair of diffuse seismicity clouds at the inside corners of the intersections between the intra-transform spreading centers and the transform fault. And so with these observations, we infer that brittle deformation of the deep seismicity clouds is associated with enhanced fluid circulation and melt depletion. due to the three-dimensional effects of the multi-segment transform faults and those local small-scale plate rotation within the Quebrada system is necessary to sustain the intense seismicity inside the diffuse seismicity cloud. So, the second part, I will briefly talk about the seismic behaviors along the Goldfarb transform fault. Because of their close in space, however, the Goldfarb transform fault behaves very periodically for the large magnitude seismic events. And there are actually two experiments that were designed to capture those large magnitude events. One on G3 in 2008 and one on G1 in 2020. And okay, so with those obvious data, let's see why these two faults has such such predictable seismic behavior. So we adapt the same location procedures as the Quebrada study, and these two maps showing the final earthquake locations on G3 and G1. The seismicities are located pretty well aligned with the actual fault trace. And here I'm showing you the seismicity distribution in depth view and also in longitude over time domain. I highlight because these two experiments actually captured two magnitude 5 to 6 events. I marked the time of the two main shocks during each experiment. You can see the increase in seismicity after the main shock, which we call aftershocks. And these two faults actually show very similar microseismicity behavior. A significant feature of these two faults is that it has these two columns of seismicity next to the main shock rupture area, which we call the barrier zone, because it seems like to stop the rupture of the main shock. The barrier zone behaves very similar along these two faults. It has intense seismicity before the occurring of the main shock, and the seismicity seems to be shut down after the main shock. And in the depth view, the barrier zone, the seismicity is much shallower than the main shock area on both these two fault segments. So these structural behavior indicating that there are some similarities between these two faults, and these similarities might contribute to the predictability of large events along these two faults. Also for G3, we observe an intense seismicity just about 7 days before the in the barrier zone before the main shock was characterized as a foreshock activity. However, on the G1 segment, we didn't see intense increase in seismicity in the barrier zone right before the main shock. However, we somehow see a decrease in seismicity in the eastern end of this barrier zone before the main shock. We can, yeah, sure. Here is a zoom in view of the foreshock activities on G3, where I highlight the location of the foreshock on G3 here. And the main shock is actually located about 0.1 degree away from the main shock epicenter location is about 0.1 degree from the foreshock, which indicates that the starting of the main shock doesn't have direct relations to these to the foreshock activities in the barrier zone. However, on the G1 segment, it shows a completely different behavior for the fall shock. This map showing the seismograph on one of the OBS stations. Time 0 is the onset of the main shock, and about 7 minutes before this main shock, we started to see intense fall shock. So this event is preceded by imminent fall shock activities. And you can also locate those events, and they are shown here in these maps. These big dots represent the location of the main shock, and the smaller dots represent the location of the fall shock. The main shock is located at around 2 kilometer depth, and it's preceded by smaller events that are very close to the main shock activities. This might indicating some preparation process of this main shock of this big magnitude event. So compare. So I don't have this very decisive conclusions for this part. Just comparing the two segments. So we do observe some common features between these two faults. For example, high seismicity rate before the main shock. In the barrier zone, we see high seismicity rate before main shock and decreasing seismicity after the main shock. And in the depth view, we also see the barrier zone is characterized by double layers of seismicity. And for the main shock, they all nucleate to the western edge of the main rupture area and propagate towards the barrier zone. But there are distinct differences between these two faults. First, for G3, we observe that its fall shock starts much longer, about 7 days before the main shock in the barrier zone. But for G1, we see an imminent fall shocks about 7 minutes before the main shock near the hypocenter. And for G1 in the barrier zone, we observe a decrease in seismicity to its left hand. So these observations provide some possibilities for us to investigate why earthquakes are so predictable on these two faults, but also need more detailed investigations to figure out why they are so predictable. So with that, I would like to conclude with the same image as the beginning. So the oceanic transform faults it can provide insight into plate tectonics, earthquakes, volcanics, that many things that we care about online, and with more multi-geophysics observations of the transform of the rate transform system, we can have a better understanding of plate tectonics and geodynamics. So thank you, and I'm happy to take questions.
Thank you, Jianhua, for the wonderful talk. Now it's time for questions. Please type in your question in the chat box, or you can raise your hands and make sure you unmute yourself before talking. It looks like John Orcutt has a question. John?
Hi, that was a very nice talk. I missed it at the beginning. How long are you able to keep the OBSs operating on the seafloor? How long were you collecting data?
Yeah, so it's
Go back to
yeah, so for this experiment, yeah, for this experiment, the battery, because some of them are short period, and the battery start to run out of power in August, so it lasts for 7 months. But this only occurs for this Quebrada transform fault. For the Gopher and Discovery, the OBS works for the whole year.
All right, thanks. No, it's very, very interesting. Lots of new and good data. Thanks.
And a question from Jessica Warren.
Hi, Jianhua. That was a great talk. I really enjoyed seeing it, and it's nice to see the Quebrada data after all these years. I was wondering if you could comment a little bit on the depth distribution of the seismicity on Quebrada, because at GoFar it seems to relate, the deeper stuff is where there are not the big main shock events, but Quebrada doesn't seem to care about that. Do you have comments on that?
So the depth. Okay, so for example, on Q1 and Q4, I think the seismicity within the diffuse clouds are special. So it doesn't represent the seismicity on a fault surface, so we exclude that. And for those seismicities that are really on the fault trees, and for Q4, we see they are roughly about a 5 kilometer depth. And on Q1 is a similar 5 kilometer depth. So it seems like it seems normal to me, this depth. But on Gopher is we do see these very shallow seismicities. For example, in the barrier zone, it can extend to 2 kilometer depth, which is not observed on Quebrada. And I do think there's something special going on in the barrier zone that caused the shallow seismicity. And for the main shock area, the depth is also around 5 kilometer depth, which is at I think it's at a normal depth range. So in general, I do think that there's something special going on within this barrier zone that caused the difference in seismicity depth. Is that answer your question?
Yeah, thanks. I mean, I guess it's not necessarily what I would have expected because you don't have any of the large events on Quebrada, but I also like your comment that it's something special going on for G3 in the barrier zone. Yeah, that sounds good. Thanks.
Question from me.
Yes, nice results. It seems that from this figure, there is some periodicity in the earthquake occurrence on different parts of the fault. Was a period of maybe a couple of months. Is this real or is this some data artifact?
Yeah, this is actually so this the western part of this G3 fault, it actually is like a swarm. Okay, so it has a big swarm occur in December, and before that, it has like very periodic behavior. I think I have a backup image.
One slide before you can see the symmetry.
I can show this first. Okay, so I just like flip the plot. Yes, as you mentioned, it's very periodic, and if you plot the daily seismicity rate in this swarm zone area, it's also very. It shows this periodicity much clearer, and I think the period is about 25 days to 27 days. I'm not sure that's correlate with any oceanographic signal or not. And also the location of the seismicity is very close to the ridge intersection. So it's perhaps there are a lot of magma activities together with flow circulation that cause these positive periodic behavior. But it's some interesting signal that we are looking at, but we don't really know the cause of it yet. If you have any thoughts on this, please let me know.
Yeah, I also noticed that there are some periodic streaks further down. So this would be at a different place along strike. I'm not sure if this is closer to the ridge or not.
So this will be, it's around 105.8, so it's a little hard to see.
Yeah.
But it was the western part, eastern part of along this fault.
Okay. I also have another comment. I'm a little puzzled by your interpretation that lack of seismicity means that that particular segment of the transform is creeping. From what we know, at least based on land observations, is that creeping faults are typically very seismically active in terms of microseismicity, and faults that are locked and are able to produce larger events may or may not have microseismicity associated with them. So I think it's a little dangerous to make the conclusion that this part of the fault is creeping just based on seismicity.
Yes, you're absolutely right. I think it's better if we have some like geodetic measurements, especially along this Q2 segment to confirm that whether is it just slipping aseismically without generating much seismicity events. So like if I could do another experiment, I would put more stations around this fault, and if it's possible, we would like to do some geodetic measurements as well.
Okay, thank you.
Well, on Yuri's comments, there is a longer term earthquake catalog for the region, which is from Hydrocom actually. And what has been reported in that study is that the Q1 and Q3, Q4 all have earthquakes during 17 years. Is that correct, Jianhua? 17 years catalog. But Q2 didn't have or have like very few seismic events reported in that long-term catalog. Now, because it's all like moving, something has to accommodate the plate deformation. And so this is one of the speculations, I guess. But like you said, we don't really know.
So this could be just a very unusually long open period, right? Or it may be creeping, in which case it will be highly unusual in that it doesn't have any micro earthquakes. So I think.
Right.
Adrian?
Hi, thank you, Jianhua. This is a basic question, but I did not realize that there was a bathymetric low at the spreading center for low spreading rate ridges or low spreading rate centers. And I was curious, why are these different than the fast spreading rate centers, and how far away from the spreading center do you go before the bathymetry starts to decline again, you know, with age?
Oh. Well, I have to, I guess I have to say I don't really know too much details of the reason. I should apologize for this. But I just know like these are two characters of the slow and fast spreading ridges. I think there are quite a lot of famous models to explain this, but sorry, at this moment I couldn't.
Oh, that's okay. I just, the picture in my mind was the right picture with, you know, a topographic or bathymetric high. I didn't realize there was a different characteristic for slow spreading. Thank you.
Actually, I also have a question about the earthquake distributions on Quebrada. Can I go back to that slide?
Yes. like a Matthew?
Yeah, Matthew. Yes. So my question is that it looks like on both, especially on Q4, the west road segment, many of the earthquakes are happening off the fault, or at least off the fault trees plotted in this map. Why is that? Is that a location error, or is it's real?
So like, I think because of the sparse seismic like station distribution, um, there can be some location bias in the final result.
Okay.
What we did is we have done some resolution tests. So just like the tomography checkboard, if we assume the earthquake is located here, and we generate some synthetic
Yes.
arrival times and do the immersion on those arrival times, and they can be located back with our location procedure and the tomorrow and the velocity model that we use. But this is not there's not a firm answer to say that these are correct. But however, we do find that for example on Q3, the seismicity seems to follow the topography well. So at certain locations, we think we see the seismicity follow the topography, and at some locations they don't. So if they are true, it might indicate that these fault trees may actually like deepen towards the south.
Okay, so it's a dipping fault.
Yeah, and another reason that I want to talk with Ross is so the fault trees is selected by some like topography features that I manually take in QG software, and it's possible like those things between the blue line and the seismicity are because of mass loss. So it may be a fault, and then there are some materials falling down, and I'm actually drawing a trace at the foothill, and the actual location of the fault is south of that. And in that case, it might indicating that this actually marks the location of the fault of vertical fault trace. So there are two.
Okay, so in that case, the fault location on this map would be wrong.
Yes, because these fault traces are drawn purely by the bathymetry.
Right. Okay, thank you. So if there are no more questions, let's just thank Jianhua again for her wonderful talk. And everybody, happy Thanksgiving. And next week, I think we're going to have another postdoc of ours to give talk. It's Jamie B. Miller.
Yeah.
Is that right? Yeah, great. Hopefully everybody will stay tuned for that. Bye, everybody.
Thanks, Jianhua.
You
Happy Thanksgiving.
Thanksgiving.
Stop it now.